that's sweet. That's a nice picture. Thank you.
All right, somebody's special day, so sing along with me. Happy birthday to you. Happy birthday to you. Happy birthday, dear. Happy birthday to you. And what really takes me to is all the cards that I got for my birthday. You guys are so awesome. You should see these. They're so cute. Okay, so we've got the card game rolling. I'm going to get it going. Okay, are there any outstanding questions before I get going? I'm actually going to switch gears. I'm going to go into my lecture, what I call my lecturing mask. You guys can't look. I'm changing. No peeking, dang it. Not in my hair especially.
What?
Good.
I have a question.
So you have a question?
Yeah, Dr. Ford asked.
Yeah, I said if you have questions. Oh, sorry. Okay, yeah, go for it. Ask.
Oh yeah, do you prefer dogs or cats?
Well,
I asked about the color last time.
it depends. So I kind of think that I like the behavior of dogs rather often, unless they're really skittish. I like them to just kind of put their head on your lap or whatever, but I don't like the ones that scratch. But cats, on the other hand, they're really sweet. However, cats can be, well, both dogs and cats can be too hairy. Yeah, anyway.
That was the correct
Other
answer.
questions? Yes?
So, like, is it actually your birthday?
Yeah, it is.
Oh my gosh, happy birthday.
Yeah, I wasn't making that shit up. But, sorry.
I once had students.
You know, my birthday is actually next week on this day.
Oh, really? Nice,
Yeah,
nice.
so we're pretty close.
Okay, so in all actuality, I'd like to give Josh a present, and that is to resolve an issue which he brought up at the end of the last lecture after everybody had left, and this is having to do with the notion of compact versus non-compact. So he pointed out something which, to me, is pseudo-obvious, but not entirely clear to how to handle it, and I found an interesting way. So last time we talked about how if you have a group which is the element, by the way, can you hear me over there on Zoom? Okay, good. If you have a group which is controlled by some continuous parameter, this is for continuous groups, I said if the continuous parameters take on a finite range, say you got rotations which go from 0 to 2 pi, then it's a compact group. If it's a non-compact group, then they go from minus infinity to infinity. Okay, that's not actually the best way to say it. The best way to say it is the following. If the range contains the limits, then it's compact. Otherwise, it's non-compact. Now what this means, of course, is that if I choose A and B on the real line, and then I just take the line interval from A to B, including A and B, then is this compact or non-compact? Oh, shoot! Liam. Compact or non-compact?
Compact.
Compact. Shaylee. What about that one? So based on what I said last time, you might think it's compact because these are finite, but A and B are what it limits to, but it doesn't actually include A and B. That's what the semicircle brackets mean. Okay, so if I'm doing A to B with square brackets, that means you go anywhere between A and B, and then you include A and B. But if it's got these circular brackets, then you go anywhere between A and B, all the way out, almost to A and B, but you don't include A and B. So this is actually non-compact. Now, anytime your limits are infinity, hold on just a second, hold on, anytime your limits are infinity, it's non-compact because you can never include infinity, okay? But this brings us back to this one. We argued that this was compact. Can anybody support the argument that that's compact?
Still technically includes 2 pi since 2 pi is equivalent to 0 in that.
Exactly. This is not on the real line. Rather, this is on the real line modulo 2 pi. So even though you don't include 2 pi on this end, since 2 pi is equal to 0, it's in the set. Okay? All right, now for us, mainly the only thing that will matter is if things are included or not included in the limits, and that's going to be an observation that we'll make possibly a little later on today, but if not, next time. Somebody had a question.
You answered it.
Okay. All right, so that's, thanks to Josh for bringing that up. And now let's dig into today. Oh, need a question holder thing. Okay. So far, we have talked about transformations. Transformations are elements of a group. And we talked about representations of transformations. Something really stinks, and I think it's my mask. Yeah, it's my mask. This is terrible. I don't know where I stored this mask, but it's, This is the one that Minds gave me.
Oh.
Yeah, obviously stuff stood in Minds storeroom for a long time. Now it smells like, anyway, that doesn't matter. Okay, so now we've talked about transformations. They're elements of groups. You can talk about how the transformation acts on something by what representation it's in. Now we're going to go back to the story of how do we make an invariant. Because at the end of the day, we're going to be interested in symmetries, and symmetries are when you do a transformation on something that's made of stuff, and that thing does not transform. Okay? And of course, the key part of that story is the Lagrangian. So you might guess that to form an invariant, we need an oppositely transforming object. Okay, so let me give you an idea of how this is going to work. So if we have an element A on the set of transformations G, G is a group, okay, and it might be continuous, it might be discrete or whatever, it doesn't matter, but if A is an element of G, then we might have a representation R which transforms by AR. A acts on R. And this just depends on the actual action of A on things. So this is a bit abstract. Okay? Now, for any matrix representation R, we can form something called the dual representation. Which we will call R twiddle. And R twiddle is such that R twiddle goes to, if R goes to AR, R twiddle goes to A inverse transpose R twiddle. Okay? Oops, jeez. Okay, so now if this is a matrix representation, then A is represented by a matrix. And then this is represented by a vector. So this is just ordinary matrix multiplication. And then this, so too is this. Okay? Now, is this what you might guess for the transformation of R twiddle? No, but watch. Here's the interesting part, and we're going to see this play out in detail in our formulation of special relativity. If all of this is true, then R twiddle transpose R, under the transformation by A, goes to A inverse transpose R twiddle transpose AR. Okay? I just put in the transformation of R twiddle, but we're transposing the whole thing, so there's a transpose on the whole thing. and then I put in the transformation of R. R goes to AR. Okay? You guys hear that? What's the hammer in the other room? Jeez.
It's a vacuum.
Oh, it's the, oh, yeah. Well, maybe they'll come in here and sweep. We got some stuff on the floor. Will you go get them and ask them to come in here and sweep, please? No, I'm just kidding. I'm kidding.
I think it's a vacuum. I don't
guys
think
gotta
they
laugh.
sweep with a vacuum.
Okay, no, here we go. Now, we're going to do a number. You guys like to dance? Yeah, you do. Come on.
Let's go.
I call it the transpose dance. Woo! Baby. Who's going to do the transpose dance? Okay, now if you're transposing a product of things, how does that decompose into the transpose of each of them? Oh, let me pick a card. Andrew.
I didn't understand the question. Can you repeat it?
I'm transposing a bunch of things. How does this reduce to the transposes of each of them? What step do you have to make?
Flip it, right?
Yeah, you flip them, okay? So this is going to be our twiddle transpose, A inverse, transpose, transpose, A, R. Oh boy, let's pick another victim. Drew. Drew.
That's me. That one is just A inverse.
This is just A inverse. Well, what's A inverse A?
I.
I. So this is just R twiddle transpose R, which is what we started with. So this is the formal procedure for setting up an invariant if your group action is by matrix multiplication on a vector. Okay? That might look weird, but it ain't. After all, if I gave you a vector and I said form an invariant out of this, what you would do is you would say, how about this? But secretly, that's this. Where you have to do this transposition. This happens to be the dual. I'll talk about the elements of the dual in just a minute. But really and truthfully, this machinery incorporates stuff that you've already seen for vectors and taking the vector and forming a scalar out of it. Okay? Yes?
What if it's like some sort of goofy integral differential operator?
So that's, well, it depends. Well, you can almost always put them in matrix form, in which case you can use this to form an invariant.
Okay.
We're not actually going to be working with those in this class. We're just going to be working with straight up vectors, so often 4-component vectors. But you could definitely do that with these crazy operators that we talked about in math phys.
Alex,
Yeah.
can you explain how you went from on the right hand side of the R tilde transpose R? How you got that, yeah.
How I got from here to here?
No, just the A inverse transpose R for all through the transpose. Yeah, just
Well, I just, so we could say, okay, so what I could say is that I'm going to send this to R twiddle prime transpose R prime. R prime twiddle is this. R prime is this. And then I'm just
Okay,
transposing
I see.
this.
yeah.
Makes sense? Okay, other questions? Yeah.
You seem to be doing a lot of transforming to have it not make a change.
To not make a change?
Yes, to get back where we started. Like,
Yeah, so I have to say this story will become much more obvious by hopefully the end of this lecture, where I'm going to bring forth some transformations with which you're very familiar. Okay, so let's stave off trying to explain that until the end, and then if you still got questions, bring them up. Okay? So now, the interesting observation is, if I have a representation R, and I have the dual, then I can always form a symmetric thing like that. But how do I get the dual? How do I get the dual? And the answer to that is as follows. A metric, G, is a map from an representation R to a corresponding dual element R twiddle. And note, this will be important to note, G is a symmetric matrix. So what we have in mind is that R twiddle is just GR. Okay? Now we'll talk about what the metric is in a minute, but right now in this abstract context, I can just say if I want to form an invariant starting with R, I need to also build R twiddle. To build R twiddle, I just take R and I apply this metric G. Okay? Now,
I have a question.
yeah,
So is small g connected to big G?
no. Big G is the set of elements of the transformations. This is actually going to be, we're going to give this an interpretation in a minute where once I give an interpretation, you'd never confuse it with that. But that's one of the reasons I gave it little g and big G, just they're distinct.
Just want to make sure.
Yeah. I mean, big G here is for group. Little g here is for metric.
Okay.
All right, I hope it makes more sense here. Awesome, sweet. Now I mean, this is actually the classical notation for metric. Normally it's got two indices, and we'll add those indices later on. Yes?
Why does G need to be symmetric?
It just is symmetric based on the definitions I'm going to give you in a minute. It doesn't absolutely have to be, but in the context where we'll work with it, it's always a symmetric matrix. Okay? All right. Now, based on this information, if we want R twiddle transpose R to be an invariant, we can now figure out something about the metric G. That is, if R twiddle is just GR, then I can write this. This, of course, is R transpose G transpose R. And now, and again, if this is supposed to be an invariant, then this should also be an invariant, but now we can do the transformation of this. And if we do the transformation of this, what we find is, now we're transforming R, not R twiddle. So this is just AR transpose. G transpose is related to G in what way? Skylar.
They should be the same.
Say it again?
The same,
Why?
because it's symmetric.
Yeah, it's symmetric. G is symmetric, so G transpose is just equal to G, and then R is AR. If we do the transpose dance, whoa, really broke my leg on that one. Look at this. Okay? This is screaming at us that if this is equal to what, then this will be invariant. No?
Oh, sorry.
Well, it just has to be equal to G, or G transpose, it doesn't matter. Okay? So what we find is an incredibly important formula that ATGA equals G as long as the G behaves under the transformations A, which are elements of the group, in this way, then this combination will give us an invariant. Okay? Now this is going to give us some insight into what G is in just a moment, but this can be used in two ways. Okay? One way is we can say, given the elements of G, so if I call these, oh gosh, I really want to write my name because it's my birthday, but I shouldn't write my name, I should write the lambda. Lambda i's. So I just have a set of transformations which are indicated by lambda. If I'm given G, then I might find the metric by solving this equation. Does that make sense? Alternatively, I could be given the metric G, and then find the transformations. Okay? So, I mean, this has got two unknowns in it. It's got the, sorry, I guess the transformations here would be lambdas instead of A's, but it doesn't matter. I'll call it lambdas. Okay, but there's two unknowns here. There's the lambdas and there's the G's. They're both matrices. I can give you the lambdas, and from that you can extract what G is, or I can give you the G, and hopefully from that you can extract what the lambdas are. We're going to do both in two different contexts. And trust me, this is going to be very, very straightforward. It's going to be something, at least the first example will be something that you've all definitely seen like crazy. Okay? So we're going to start here, and we're going to end here. All right? So let's start with knowing the transformations and then asking what is the metric. And I am going to hammer on an example with which you all should be incredibly familiar. How about rotations in 3D? You guys know a little bit about that? Yeah, it should be to a certain degree of pain. God dang, I hate them. What's our G look like? Well, first of all, the group of rotations is a compact because no matter how you parameterize it, the angles always take a finite range, so it's compact. It's continuous because the angles always take a continuum of values. It's a non-abelian group. So if you do a rotation around different axes and then you reverse the order, you often end up in a different state. And we can denote the transformations roughly. There's an infinite number of them, so if I want to write down all of the elements, it's going to take a while. You guys got time? Really?
If that's how you want to celebrate your birthday.
Are you going anywhere ever? Wait, it's an infinite number.
Well, then do it fast.
Okay.
You better start now.
Theta.
Rotation by x, 0.00000000000000.
I think you missed a zero in between the zero and the other zero.
We're not going to do this. Okay, no, in all actuality. So there's a way to treat these sets of infinite transformations, which we're not actually going to delve into, but it's very useful. That is to realize that even though there's an infinite number of transformations, you can usually pare it down to a handful of transformations which are defined over an infinitesimal, and then to build any transformation, you just take an infinitesimal and you just compose it with itself. So you can imagine that you could start with a rotation in the x around the x-axis by an angle theta, where theta is ridiculously small, I mean infinitesimally small, and then to get any higher angle theta around the x-axis, you just multiply these together until you get that angle, okay? But you should independently do a rotation around the y-axis, which might be parameterized by an angle phi, and then a rotation around the z-axis, which is parameterized by an angle psi, okay? All right? This is one way of breaking it down. There's many others for the group of rotations, but for my purposes, this is fine. Now, what we want to do is we want to consider two objects in space whose coordinates are given by xa, ya, za, and xb, yb, and zb. Oops, b. Okay? Now, hopefully, it is obvious that if I take these 2 points in space and I consider the distance between them, This is a scalar. This is not the vector, the displacement from A to B or B to A. This is just the scalar magnitude of the distance between them, or the magnitude of the displacement vector. Okay? That scalar should be an invariant under rotations. Everybody on board with that? Everybody on board? Okay, so let me write down an expression for the invariant distance, delta S. This we can write as xa minus xb squared plus ya minus yb squared plus za minus zb squared, all square root. Okay? However, just to make our life simple, because we really hate square roots, we should probably just think of that as the square of the distance between them. If delta S is an invariant, so too is delta S squared. So we might as well work with delta S squared. That way we don't have that square root sign. Okay? And we can, of course, write this more compactly as delta x squared plus delta y squared plus delta z squared. Shoot, I don't know why I put the square root back on there. Okay? And now I want to deconstruct this a bit. Consider, instead of writing it that way, let's write it like this. Delta x, delta y, delta z, delta x, delta y, delta z. Okay? All right, obviously if you do this matrix multiplication, you just end up with this expression. Everybody on board with that? That's just breaking this up into two factors using matrix multiplication. Now what we want to do is we want to rotate. So if we rotate, then we know that the vector with components delta x, delta y, delta z will become the new vector delta x prime, delta y prime, delta z prime, which is just a rotation matrix acting on the original vector. Okay? We good? And we know what these rotation matrices look like. You can probably pop one out for two-dimensional rotation. If you think about it, you can probably pop one out for 3 dimensions as well. Okay? Now what I want to do is I want to make the observation that if this is the case, then delta x, delta y, delta z must transform in the following sense. This should become delta x prime, delta y prime, delta z prime, where this is now equal to r delta x, delta y, delta z transpose. Okay? So now, if I explore the invariance of delta S squared, again, it can be written in this form, but now, if it's invariant, then I can say that this is equal to delta x prime, delta y prime, delta z prime, times delta x, delta y, delta z, sorry, primes. Okay? But now I can replace this with this, and I can replace this with this. Let's do it. Okay? So I've got, well, let's do the transpose dance, folks. Okay, well, I got one person here. That's good enough. If we do the transpose dance on this, I'm going to transpose this. That's going to give me delta x, delta y, delta z. And then I've got to transpose r. And then this thing is just r times this. So, here we go. Sean, are you here? Sean. Sean. If I want this to be equal to this, what can you tell me about this?
R transpose R is the identity matrix.
Exactly. Now Now, many of you have probably seen this condition for a rotation matrix. Okay, they're called orthogonal matrices. But here's what I want you to observe. Are you ready? We started with the set of transformations that we know, the rotation matrices, and we're looking for G. Jared. What's G?
R transpose R.
So R is playing the role of the transformations lambda.
Yeah.
They just happen to be rotations, so I called them R. That's just a given. You can phone a friend if you need some help. I mean, what is on the right-hand side?
I guess I'm not sure what you're asking.
Well, I'm asking you, what is the metric G that arises in this expression?
Yeah.
You got a friend in the back? Follow him. Go for it. G is the identity. G is sitting by itself on the right, and I is sitting by itself on the right. Now that's screwed up, right? Because G also has to sit in here. Is G sitting in here? Hell yes it is. It's the identity. We just never write it. So in principle, we can understand this expression as IR equals I, and then immediately conclude that G is the identity. That is, its matrix form is 1, 0, 0, 0, 1, 0, 0, 0, 1. There you go. This is undoing one of the first vector manipulations you ever learned. You learned that to take the dot product of a vector, you just take the x components and you multiply them by the y components. That is crap. You must introduce the identity matrix as part of the story, for reasons we'll see in a moment. Okay? But your math teachers never, they never really changed this away from the identity, so they're like, oh, we'll just leave that matrix out. They hate matrix multiplication anyway. Right? Okay? Okay. Now, hopefully, well, actually, let me give you a reason why we call G the metric. G is the metric because if we take coordinates and use them to label points in the space-time, then you're not necessarily associating a distance with a coordinate change unless you combine vectors with a metric. In this case, the metric is so trivial that it doesn't really seem to do anything, but let me give you an example where it does. And this will be a good example of why G incorporates the notion of distance in a way that coordinates by themselves don't. So imagine if, I'll leave that up there. So imagine if we were in 2 dimensions, if we were in 2 dimensions working in polar coordinates, so in 2D, imagine working in polar coordinates r and theta, okay? ds squared is dr squared plus what?
dr d theta squared?
Well, what about just d theta squared? That's like what we did before. We just took the differential of this, the differential of this, right? Is that wrong?
That makes me feel some sort of way.
Good. What should this be?
Should be r squared.
Exactly.
Oh, heck.
Okay? So, well, hold on. If my vector of infinitesimal differentials has components dr d theta, what's the metric?
2 by 2 with 1 and then r squared and then bottom right.
Exactamundo. So you've certainly encountered situations where to put together an invariant, you need a metric which is not the identity. Okay? Everybody clear on that? We're going to see many, many examples. I mean, we might as well just dump the identity because we're never going to see it again. Starting with relativity. Okay? All right. Okay, good. We're actually doing pretty good time. All right. Whew. Now, special relativity. And I'm not done with the story. Remember, I was going to do one thing and then I was going to do another. I'm about to do the other. Okay, I'm about to do it, but I'm going to define special relativity for you first. And that is the statement that physical laws should not change under transformations continuously connected to the identity. That's just an additional detail, which we won't worry about. Which preserves space-time intervals of the form delta S squared equals minus C squared delta T squared, or I can just do D, doesn't have to be delta. We're going to largely use differentials plus dx squared plus dy squared plus dz squared. Okay? It turns out that if you give me the preserved length, you're giving me the metric. What's the metric?
The Minkowski metric?
Sorry, say it again?
Minkowski metric.
Yeah, it's the Minkowski metric. So in particular, we've got to write down what our vector of differentials are. And our vector of differentials would be c dt. The c is just thrown in to make the units agree on all the terms. So they're all distances. Okay, so t obviously is measured in seconds, but if you tack on a c, it's going to come out in meters. So c dt dx, yeah, dy dz times the metric times c dt dx dy dz, and the metric that's required as a matrix is minus 1, 1, 1, 1, with zeros everywhere else, which, as Ross pointed out, is what we often call the Minkowski metric, which we give a special letter to eta. This is the only metric that we're going to call eta. Okay? Now, given the metric, we can take lambda transpose eta lambda equals eta as our starting point and figure out, okay, what kind of transformations does this define? Does that make sense? So we're going to do the opposite. We're going to start with the metric, and we're going to use this expression with the metric to uncover what are the transformations lambda. Yes?
So why are we interested in ds squared?
Why are you interested in ds squared? ds is, so we're going to come to this in time, but ds is sort of a prototype vector. It is the vector which should exist if you have a space with distance at all. You don't have to have any other fields on it. The other vectors that you encounter are often either field vectors like the electric or magnetic field, or they're vectors which are built from ds, because you can get the velocity vectors, the momentum vectors, and so forth and so on. But this is going to play the role of the defining vector for us in addition to just a distance measure. And we'll see plenty of that as we proceed into extending all this to curved spaces. Okay? So now what we're after are the lambdas. What are the lambdas? Okay? Everybody on board? So let's bang out some of the lambdas. Well, hold on. So, oh, wait a minute. Hold on. This contains this, which is just this part of the metric hitting the dx, dy, dz. So, if I set dt to 0, then all I've got are these spatial distances. What kind of transformations do not change dx squared plus dy squared plus dz squared?
Rotations.
Rotations, that's what we just talked about. Okay? So we know that a subset of the lambdas are just rotations. So we can say that our lambdas include a rotation around x by theta, a rotation around y by phi, and a rotation around z by psi. So what do you think we have to add in? A rotation around t. Yeah. If we just add in a rotation around t by, I don't know, beta, then that's it. That's going from 3 dimensions to 4 dimensions. That's awesome, isn't it? Don't even raise your hand. It's the biggest bunch of bullshit. As many of you who are in SPS know, or have taken a class from me before, this is one of the worst lessons that you can teach people. And that is the idea that you should imagine a rotation around an axis. That is crap. It just so happens that in 3 spatial dimensions, and only in 3, a rotation in the YZ plane can be represented by a rotation around the x-axis. So too can a rotation in the ZX plane be represented by a rotation around the y-axis. Okay? Well, let's do a simpler version. 2D. Can you describe the rotation in the plane as a rotation about an axis in the space? No, because there's no 3rd dimension in this space. Better still, let's do 4 dimensions. If I pick the plane that I'm rotating in to be the YZ plane, how many vectors are there normal to the YZ plane? Well, there's at least 2, x and t. So if I'm rotating in the YZ plane, am I rotating around the x-axis or am I rotating around the t-axis? I don't know. But what I do know is that I'm rotating in the YZ plane. And that is how I should understand it. Do not get fixated on rotating around axes. Fixate on, I rotate in a plane, a 2-dimensional plane. That's how I define it. Therefore, for the rotation part of our story, I should replace these with rotation around in the YZ plane, rotation in the ZX plane, and rotation in the XY plane. And now, hopefully it should be obvious what I should add onto my set. How many generating transformations? 3. I should have a rotation in the xt plane parameterized by beta x, a rotation in the yt plane parameterized by beta y, and a rotation in the zt plane parameterized by beta z. Okay? Does that feel right to you all? Good. to say, what is a lambda which corresponds to a rotation in the YZ, ZX, or XY plane, given this is my structure, can anybody guess one? So let's, for example, do a rotation in the YZ plane by an angle theta. Okay, what do you think that matrix looks like?
My answer, everyone, or?
Go for it.
Oh, well, it's going to, oh, sorry.
Go for it.
Okay, so it's going to be like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, cosine theta, negative sine theta, and then 0, 0, negative sine theta, cosine theta.
Yes.
Oh, I ignore that because it's so much.
Yeah.
Is that one supposed to be there?
Okay, folks.
Oh, and I think there's actually an extra 1 in the first column.
Oh, sorry, yeah, you're right, thank you. Okay? Folks, this is just a 2 by 2 rotation matrix that's acting in the YZ plane. So this is what we would call a rotation around the x-axis. It leaves a vector along the x-axis invariant. Okay, and then the time is just riding along with an identity. Okay? Everybody on board with this? It's just an example. You can bang out what a rotation in the ZX plane is, what a rotation in the XY plane, just by moving the sine and cosines to various points. But all of that happens in the lower 3 by 3. Okay? Now, hopefully it's obvious, but perhaps not. But if we take this and we transpose it, and we multiply it by the metric eta, which is again given by minus 1, 1, 1, 1, and then we multiply it yet again by the matrix, what we end up with is the following. Oh God, there's too many of these. Oh, there we go. Okay. This is really just, transposing this and then multiplying it by this and then multiplying this by it again. Yes?
Is there a reason the first lambda is YZ and the second is Y?
Oh, sorry. Sorry. Yeah, they're the same. It's the same transformation that you put on each side of this. Okay? Wait a minute. Anybody see a simplification? You guys see it? What is this? It's just eta. The diagonals become 1s and these become 0s. So this is equal to eta. All right? Yes?
So it seems like for a metric, we could have done anything that only has entries on the diagram. We have the particular one we have here.
Hold on just a second. Say it again.
It seems like this would work for any metric where we only have entries on the diagram. So why do we have the particular one we have here?
So if we had a diagonal metric, then it seems as if this transformation would work for any diagonal matrix? Diagonal metric.
It seems like rotation either only works with the metric being the identity, right? Because they invert themselves, and so whatever you put between them shouldn't get in the way. But it could also be the case that it works with anything that has stuff along the diagonals, because then those just multiply out into the matrix to the front, and that's how you get there.
hold on, what do you mean? So are you talking about an overall coefficient of a diagonal matrix, of the identity, or are you talking about with different elements along the diagonal?
Well, in other words, it seems like as long as your entries for your metric are only
On the diagonal.
it would work for this, because none of the weird matrix stuff happens, you can just move it to the front, and it would still be itself, and be multiplied. I don't think
Trace
that's
on the
a
diagonal
big
wouldn't
deal.
work for this, I don't think.
No, I see what you're saying. And
That lambda doesn't work with the eta with different entries on the diagonal, I don't think. Because the cosine beta minus sine beta cosine beta wouldn't go to 0 anymore.
yeah, that's
There'd be
true.
different coefficients
That's
and
true.
stuff.
Yeah, because so if we actually did this multiplication out, you would notice that these things which are canceling to 0 are incorporating different elements of the diagonal of eta. So I encourage you to do this matrix multiplication. And you can actually go and put in A, B, C, D along the diagonal, and you'll see that these cancellations won't happen. Okay, I could have written it out, but it's taken like too long. Okay, but that's the answer to your question. Okay. All right, so, okay, now, yeah, okay. So, for the spatial case, which is what we get by cheating and just paying attention to dx, dy, dz, we get a rotation matrix which involves sines and cosines, but hopefully you realize that this identity is what really plays an important role in these things working out, okay? Now what you can immediately wonder is, oh, there's a minus sign, okay? And in fact, that minus sign might say, well, you know, we were used to using this with dy squared plus dz squared.
Super quick clarification.
Yeah, go ahead.
If the cosines and sines and whatnot were like shifted one up the diagonal and then the second one there was moved down to the bottom.
Sorry, here?
Yeah, so the cosines were shifted up one on the diagonal and one was moved down and then the sines
Yeah.
were also shifted up. You could get one of the other rotation matrices that way, right?
Oh, yeah, yeah, yeah,
Okay,
definitely,
cool.
definitely. Yeah. Okay. All right, so I just want you to focus for a second. We were doing a YZ rotation, so we were really, this was the part which was getting mixed up. The X and the T weren't even being touched. So the invariance of this hangs critically on the invariance of this. Now my question is, what do you think the invariance of that might hang on?
It might hang on hyperbolic cosine and sine functions.
Or, yes, thank you, Ross. This can, in some way, shape, or form, hang on that expression. Okay? And really and truthfully, the reason why we would use cosh and sinh is because there's a relative minus sign in this identity. And that minus sign can take care of the minus sign here. So without any further ado, let me write down the matrix for rotation in the xt plane. It's given by cosh of phi, where phi is just a parameter, minus sinh of phi, minus sinh of phi, cosh phi, 1, 1. With zeros everywhere else. That's going to be my new machinery. I'm not going to write in all the zeros. Okay? So this is a new and strange rotation in the xt plane. And again, the only reason I'm using cosh and sinh instead of cosine and sine is because I know I need to make use of this identity. And I do in fact need the same sign on these off-diagonal cinches. Whereas with rotations, you always have the opposite sign on the off-diagonal terms. Okay? So this is not a mistake. Now, trust me, we can take this, we can multiply it by we can take the transpose of it, multiply it by the metric, multiply it by the original matrix, and that is going to give us, among other things, minus cos squared phi plus sinh squared phi times something which equals 0, something which equals 0, minus sinh squared phi plus cos squared phi 1, 1. Okay. These equal zeros are non-trivial terms. I just don't have time to write them up. They're pretty long, but they're akin to these terms. Okay? Does anybody see a simplification? What's this term? It's negative 1. It's negative 1 because minus sin squared cos squared is 1, and this is 1 with an overall negative sign. This, of course, is just 1, which equals eta. Okay? So, there you have a rotation in the xt plane. There is one thing that someone in the room should say. Oh, really? Thank you. Many of you have obviously been in my class before. This is a what's that formula moment. All right? What is lambda xt? Well, let's investigate for a moment. And this is where you will finally go, oh, okay, I get it. So, consider the coordinates, c, delta t, delta x, delta y, delta z, and they're going to transform to a new set, c delta t, delta x prime, delta y prime, delta z prime, under the action of this transformation, this rotation in the xt plane. Okay? Well, if I write it out, this is what I get. So I'm literally going to take this matrix and multiply it onto this 4-component vector. Okay? And what we end up with is cosh of phi times c, and I'm sorry, I should be doing d's, but in my notes I've got deltas. We're going to replace d's and deltas everywhere, so just bear with me. I'm not going to go and erase all my deltas and make them d's. C delta t plus sinh phi delta x minus sinh phi c delta t plus cosh phi delta x, and then delta y and delta z, they go untainted, because this thing is not doing anything to y and z. Okay? Are you ready? No? It'll be okay. Consider the frame S, okay, with the axis x. And now consider, oops, I'm so nervous, I'm trying to tilt the things. The frame S prime with axis x prime, and the relationship is that the frame S prime is moving with a velocity v with respect to the frame S. And v happens to be along the x direction for simplicity. Okay? Now what I want you to do is to consider this point in the S prime frame the origin of the S prime frame, obviously. Okay? Now follow this. Ready? In S prime, what is the delta x prime associated with the origin? So the x prime axis is moving with S prime, including that point. So how much does this point move along the x prime axis?
0.
0. Okay? All right? So what we can say is that delta x prime, which I can read off of here, is minus sinh phi c delta t plus hash phi delta x. Okay? This is 0. Therefore, I can take this and I can say, oh, wait a minute. Delta x over delta t is c times the hyperbolic tangent of phi. Just take this, move 1 to the other side, and then form delta x over delta t. We on board? And trust me, this is not something which people are like, well, I guess some people did a long time ago, a guy named Einstein. But most people couldn't do this on their own. You just read it and you kind of understand. You're like, yeah, I could maybe repeat that once. Okay? So don't be flabbergasted by this analysis. Okay, so there's your delta x over delta t. But in S, where x and t are used, the origin here, does it have a delta x? Yes, it does. Does it have a delta t? What is delta x over delta t? In these coordinates, what is the speed of the origin of this coordinate system?
V.
It's the velocity that this coordinate system is moving with, v. So in this coordinate system, we can say Vx equals v, which is delta x over delta t. Okay? Oh, wait a minute. This is also delta x over delta t. So what we can say is that v is c tangent of hyperbolic tangent of phi did you know that you can take this and using hyperbolic trig identities, which are not that different from normal trig identities, but I won't go through the details, you can tease out an expression for cosh phi and sinh phi. Okay? Cosh phi ends up being 1 over the square root of 1 minus v squared over c squared. And sinh phi ends up being gamma v over c. Where this is what we define to be gamma. So in all actuality, the transformation can be written in terms of the relative velocity of two frames, v. Okay? So what this is telling us is that c delta t, delta x, delta y, delta z goes to c delta t prime, delta x prime, delta y prime, delta z prime, which is equal to, and if I plug these in to this expression and then multiply this vector by that matrix, what we get is gamma c delta t minus v over c delta x, gamma delta x minus v delta t, delta y, delta z. Does that look familiar to anyone?
Oh, those are the Lorentz transformations.
Thank you, Ross. Those are Lorentz transformations. Do you remember seeing the Lorentz transformations in modern physics?
Many eons ago.
Now, I want you to go back for a moment. We started out by saying we were doing a rotation in the xt plane. But our interpretation of it is that a rotation in the xt plane is actually a boost along the x direction with some velocity v, relating two frames. Hopefully, it should be obvious what a lambda yt would be and what a lambda zt would be. Okay? Again, say it again.
In the first row, what's that symbol before the does x?
V over c. The velocity v over c. This right here is v over c. You good? Okay, so I have so I'm not going to keep you guys late. The end of the notes provides, from this exact same starting point, a derivation of the velocity addition formula, which I earlier on in my first lecture said is very characteristic of special relativity. Okay, it's a very short derivation, but it comes back to that, standard thing, that u prime is u plus v over 1 plus uv over c squared. Okay, where u is the velocity something's moving with in the prime mass prime, v is the relative velocity of the two frames, and then you want to know what the velocity looks like in the other frame. Okay, this result is derivable from this analysis, and I'll leave that for you to read in the notes. Okay, so do we have any final questions before we depart? Yes.
Will you be able to see everyone else's,
You got to yell it.
will we be able to see everyone else's, postcards or cards?
These?
Yeah, like which part?
Oh, yeah. So when we do our midterm, this is going to be our screensaver. Yeah, so hopefully you're brave about what you submitted. All right, are there any other questions? Yes?
Can you repeat the thing you said about rotations and boost along the x? Whatever it was that you were saying.
Rotations. Well, no, I just said that I called this a rotation in the xt plane. I shouldn't have called it a rotation because rotations are intrinsically built on this identity.
Okay.
Because we have a minus here, we need this identity, but these aren't used to describe rotation.
Okay, so it's not an actual
So it's not an actual rotation. It's whatever transformation you can do using the x and the t axis. And now I've given that transformation an interpretation. That is, I'm actually moving along the x-axis, which also changes the t part of the story as well.
And so what is phi meaning? Like what is the angle?
What is the angle? Well, the angle phi you can just write down
I think
as
so.
v over c.
Oh yeah, okay.
Inverse tangent. There's nothing intuitive about it. Nothing intuitive. Yeah.
I'm gonna go ahead and pause that.